Hi, I'm Lange from the Mesoscopic Quantum Optics Group from Paderborn University. I'm working in the group of Tim Bartling. I'm focusing on investigating nonlinear effects in lithium niobate waveguides, and I'm doing that at cryogenic temperatures, which means that I'm cooling down the waveguides to extremely cold temperatures. This graph is an evidence that parametric down conversion remains functional when operated at cryogenic temperatures. And it shows the joint spectral intensity at about 4 Kelvin, and this is the coldest temperature a parametric down conversion experiment was done so far. Parametric down conversion is a nonlinear effect. It's a frequency conversion process where one photon decays into two photons, which are called the signal and idler. And it is a standard technique to generate different kinds of quantum light, such as heralded photons, entangled photon pairs, or squeezed states. Parametric down conversion is typically performed at room temperature. There is no really need to cool it down. But we are focusing on integrating it together with other photonic devices, and there are some interesting photonic devices such as superconducting detectors, and they provide very high detection efficiencies, but they require cryogenic temperatures for operation. And to integrate those detectors together with parametric down conversion, we need to operate SPDC as well at cryogenic temperatures. There are two main challenges, I would say. The first challenge was that there was not much data available, which tells us how our material behaves when we cool it down. From our prior measurements, we could gain some important information about it, so we could find out how the refractive indices are changing, and also we could measure an effect which is called photorefraction. At those prior measurements, we did second harmonic generation, which is the classical reverse process of parametric down conversion, where two photons convert to one photon. And that gave us some important information we could use now for parametric down conversion. And the second main challenge is that we needed to think about how we can realize the experimental setup. So when we investigate parametric down conversion at room temperature, that we can typically do free space, because we need to couple in the laser pump beam and couple out the generated photons. But when we want to investigate it at cryogenic temperatures, there we need to put our sample into a cryostat, and this is way more challenging then. So for our experiment, we put the waveguide sample into a free space coupled cryostat, and that allows us to couple to the waveguide end facets through transparent windows at the side. So in the experiment, we at first generate our pump beam by performing some second harmonic generation, and this pump beam is then filtered and coupled into the sample, and on the other side the signal is coupled out again and filtered again to just keep the generated photons, and coupled into two different fibers for the signal and idler photons to allow for some further investigation. For example, we are measuring the wavelength of the photons, or the Klisch coefficient and the coincidences to accidentals ratio. Yes, so you can see here in the middle our cryostat, and our waveguide sample is mounted at the moment inside. Here on the side you can see two windows which we use to couple our beam in and out. And here at the beginning of the setup we couple out our 775 nanometer beam, and it goes here through the setup and is coupled in with the lens on that side, and we couple the beam out on the other side with another lens. Then we filter our signal and idler photons and separate them with a polarizing beam splitter at that point. And we then couple the two photons into two different fibers, which we use then for further investigation. To measure the wavelength of our photons, we employ a home-built scanning grating spectrometer setup. There we use two reflective collimators to couple our photons out of a fiber and to couple in after it again. And we use a lace grating as a dispersive element to separate the wavelength components. And by coupling into the output fiber, we can filter out a specific wavelength component and therefore remap our spectra. So in general, our experiments show that SPDC remains fully functional when we cool it down to cryogenic temperatures. And this means that although we change the temperature by nearly 2 orders of magnitude, we can still get a functional parametric down conversion source. Yeah, at the moment we've got a functional source, but we also want to have it highly efficient. And there are still some more open questions. So we need to get more data about how, example, the spatial modes are changing and also about the photorefractive effect. Yeah, our experiments can widen the application possibilities of parametric down conversion, because by operating it at cryogenic temperatures, we can integrate it together with different components such as superconducting detectors, which allows us to have a fully integrated cryogenic chip.